Okay, so what we said is we want to learn features for each word. And we said that we could do the same thing, so we learn k features for each word. So usually. Okay, so that's again. So here is my word D. I'm going to look at these k entries, which are the row. So yeah, same problem as we had before, and as said, to be very honest, we use the logarithm of these counts. The cool thing is they're just there. That's it. So same algorithms. What I have not told you yet is how to choose these weights. We said that so some of the words are weighted a bit more and some are weighted a bit less. So when they appear together. The idea is, this is always important if you do problems with text. So actually, even what we described at the very beginning, if you do this naive one-hot encoding or bag of words, then it's very important that you do a weighting of the words. Which are the interesting words and which are the boring words, which is, for example, articles de and a and whatnot. So don't do anything which is based on a fixed set of rules, but try to have a mathematical concept of the importance of a word. So the very frequent ones, the most frequent ones are boring, and the very least frequent ones are also boring. The frequency of a word is very important, and we're also going to use this here to see, well, to get the best possible representation. Okay, so what they use is a bit weird, but that's exactly what I mentioned. So you want to have an importance for a word or for two words appearing together. So basically, which of these entries, the black entries here, the white ones, sorry, how should they be weighted, right? Because some words appear together a billion times, and some are very rarely together, and some never appear together. So they came up with quite a nice way. It's very useful in practice, but it's very obscure and just a bit of engineering why you would choose the weighting that they have chosen. So what they have chosen is that here's the count of n and t appearing together. So people call this the co-occurrence count. And what they do is they take this relatively with respect to the maximum count, which is here. That makes a lot of sense, right? You should maybe normalize, so take it relative to the maximum. But then what's a bit obscure is they take this to some power alpha, where alpha is 3/2. So that's like super obscure, and then they also cut it off at the end. But this is not so important. It's just that you want to have a kind of a weighting where here is again the count. You want to have this weight kind of grow, and apparently it's a good idea to have it 0 when the count is very small. If the weight would be equal to 0, well, that would be the same as not if you look at the loss function, that would be the same that it would not take part in the loss function. Where is the loss function? It's here. See, so if this would be 0, it's just that pair of words does not contribute. We don't count it. So that's a bit the same thing as what actually is omega, right? It's everybody that counts. So those entries we have appeared together. And then here we just have, this is just the same thing as omega, but it's a weighting of it. So yeah, don't worry, there's nothing much to learn from it, except that it's sometimes good to think about if you want to use some weighting. And here it makes a big difference, it turns out. It's the same intuition that actually only using the observed entries makes a big difference. So yeah, it's like in the recommender system when the thing that you don't have ratings for, don't just put zeros there. That makes no sense, because it's not that this is the worst rating, but the information is that we have no information there. That's why it's a difference if you just count it as not contributing to your objective function, or to contribute it as 0. So that's a difference. And here people try to be even a bit smarter about how to count these things. So what model am I actually talking about? This is called a global vector representation. This was only invented, I think, 2014. So it's quite new. Even if the mathematics is not so hard, right? It's the same thing that we had before. We just factorize a matrix. So that's the same thing. But what's the smart thing is to have this idea to apply to the counts of words appearing together. And then there's a bit of engineering that these people have thought quite carefully how to do this weighting to then get even better word vectors. So yeah, this is basically one of the state-of-the-art methods for word representations at the moment, and it's basically the same idea as word2vec, which you might have heard of. That's exactly what this is. But we present this one because mathematically it's clear that it's the same as what we have seen before. And again, the algorithms to do this, to find it, is actually also the same. So if you want, you can do the text representation project. If that's interesting for you, then you could use such methods, train on your data. What's actually even better is to not train this, but just to download pre-trained vectors. So people have trained this on much larger texts than we have around usually. So people actually share these collections of word embeddings, so word vectors. So you can just download them. There is one vector per word. So, or if you're interested, but here we're also interested in understanding how it works. That's why we explained how you could train it yourself. What does training mean? Well, yeah, just finding the W matrix. And again, same question: how? Yeah, which K to actually use? That's also quite interesting. So, okay. So there are some demos online. You could actually, I don't have time to play around, but it's actually a lot of fun. So you can do some fun stuff with these word embeddings and see what is close to what. And so if you look online, there will be some very interesting observation with these words. I'll mention this in a minute again.
So you mentioned we're not interested in the extreme case, right? Either if it's very frequent or it's really not frequent. But how does this particular weight function handle the extreme case? How does it, add more weight to the regular ones, or like efficiencies?
Yeah, so this weighting function is kind of trying to remove the influences of the extreme case. That's what you're saying, and that's exactly the case. So why is it? Because here it's small, right, when you're a very low count, so it doesn't contribute much. And when it's very high, then it's not small, but it's actually kept. So it's kept at the maximum count. Yeah. Well, this part doesn't really matter anyway, because there is no word which appears more than the maximum count. Yeah, sorry, there is not much mathematically to say about this thing. This is an engineering thing. Like a lot of deep learning especially is a lot of trying things, and you could use a different weighting function, a simpler one, like the linear one, see if that works. So, and yeah, or use a different alpha. So this gives you different embeddings, but this turns out to be working quite well. But there's no understanding why theoretically this would make sense to choose the alpha to a particular value. So yeah, so this was a bit dry, just showing you the math and this very unintuitive weighting function. The more fun thing is that this actually works super well. So first of all, it's able to really, if you have a word and a synonym, which means the same thing as the other word, then they get to almost the same point, right? Not exactly the same, but they get very close. So it's very nice. You can just go somewhere in space, ask, yeah, which is the closest word to where I am, right? So that's now a possibility, and then this way you can build very good machine learning systems, which use words. So whenever this has completely revolutionized natural language processing, right? This was not around 4 years ago. So before, everybody used this bag of words, which you discussed at the very beginning. And now came this. It's quite surprising because, again, yeah, we had low rank factorizations. That's not a new concept, but the new concept is to actually apply this to do this formulation I showed you, only the observed words and on this co-occurrence matrix. It has some other funny side effects. So, for example, if you look at, now you look at 4 words, so they're somehow related, right? So you have king and queen, and you have man and woman. So these are 4 points in space. So anyway, if you are at the point man and you go to the point women, so that's now a vector in space from between 2 points. You take that vector. That's what we have here. I take that vector and attach it to another point. Let's say I attach to the point king. Then I get somewhere here. And turns out the closest word to where I am turns out to be queen, which is quite interesting, right? Because this system here knows nothing about the world or about what actually is a queen or anything. So, but it turns out that this relationship is preserved in this space, kind of that. So you can. It turns out, yeah, the closest point is queen. So it kind of understood that what that should be is what we found here. You can do this for let's say, maybe this is more clear. You have countries and their capitals, right? But these are just words, right? We know nothing about them. So, but if you just take all the text in the world and see what text appears together, do our factorization. I have a word vector for Spain, I have a vector for Madrid. Turns out they are all in the same direction for, well, almost. All the countries and capitals, they're kind of giving you one direction in space. So then if you don't know what is the capital of Italy, then you just take the vector you had from Spain to Madrid, attach it to Italy, and ask what's the closest point to where I go. So if you actually have time in the end, I can do a little demo. Otherwise, you have to try it out yourself, which I really recommend to do. It's a lot of fun. So yes, we actually do have a bit of time to play with this. So. Let's see if okay, give me one. You get a 1 minute break. Sorry for that. So. Okay, so here is this. So what has happened here is the vectors have been trained, right? So these word vectors are now, you can just download them. They're saved somewhere on disk, or you can have them. And now you can play with them. So now what we do is we give 3 points, and we do this trick, adding king to queen, or adding these 2 and attaching it to the 3rd point. Where do we go? So now we are somewhere in space where there's no word, but then we ask what's the closest word. So you can do like what is Germany? So this is not going to work because it's actually case sensitive, so, and I can't use shift, so we can try this. So okay, how this works is Lufthansa is to Germany, as is the thing we're searching for is to France. So what is this thing? Oh yeah, it's Air France. So now it finally worked. Okay. So what else do you want to do? So I can do beer is to Germany. Like what is it to France? So I am surprised this actually worked. Anything else? I'm open to your suggestions. So. You can change everything. It doesn't have to be about countries. It can be about anything.
Can we try Germany is to Switzerland?
Germany beer is to Switzerland.
I mean, Germany is to Switzerland, and then France.
Ah, yeah, okay. Germany is to Switzerland, like France is to what? Yeah, what should that be actually? What do we expect? Maybe Belgium or something? Okay, okay, sorry. That didn't work, yeah, so. Okay, I have a funny one actually, so. France, I mean, you have these interesting things like the Eiffel Tower or something. The Eiffel Tower is to France, it's a very important thing, right? So any other country we should do. So Switzerland. Yeah, I'm slow typing. So this is pretty nice, right? Because this word actually knows absolutely nothing about this. Yeah, it works quite well for many things. Yeah. Okay, this doesn't work. Yeah. I think this is something I tried once. So. This, yeah, this is a bit weird. Yeah. So. Okay, let's not get into political details. For those who don't know, there was a very strange political vote a while ago, and so this system here is trained on news. It's on okay. I take this away before you take a photo. So. Anyway. The system I showed you is trained on news documents. So there were many news stories which are mentioning these things together, right? And this is trained on things appearing together. So you can even play funny games with putting people there, then you get into more trouble territory. But this works really well, and it's cool because it knows nothing about logic or rules or something. This is purely data-driven, right? There's no additional information has gone into the system. That's why it's nice, because it's kind of unsupervised system. But it's far from perfect, right? It's not. But it's quite interesting that some things it can pick up. And the upshot from this is basically whatever has been done previously with the old school NLP approaches for text understanding. They were based on the first approach, word-based, one-hot encoding. Now you just plug in these word vectors and then keep doing the same thing you want to do on top, and you get huge improvements from doing that. And the word embeddings improve a lot. It's a very active area of research now. So again, the one I showed you is one example, word to vec. We're going to see in a second. It's almost the same. And yeah, last week Google has opened a new word embedding, so it's all publicly shared, which is nice. So people try to now really improve this, and once you have these word embeddings, you can plug them in to any machine learning task you want to do. Maybe that's also useful for some of the projects you want to do in some of the labs. We have a fun project, a semester project, where we have people 1,000 people, no, 500 people were sleeping, and we asked what are they dreaming from the EEG signal. That's quite strange. But when they woke them up, they asked them for one word which describes their dream. So, and now we're trying to see if we can predict a point which is close to the word they have been dreaming from the EEG signal. But we don't know if that's going to work. Is Etsky in the room? We have one of you is helping us with that. So, and yeah, we might need more help actually. So, okay, fun things with word embeddings. Training it, as you already said, it's the very same thing as for recommender system, nothing new. But it's quite some active research, as I mentioned. For example, how can you train this distributor? Because now you have so much data, you can use the whole internet to train. You don't need labels. So then you better have a fast algorithm to train it. But luckily, stochastic gradient descent is very fast on this. Yeah, so a problem that this has is it doesn't really take into account the order of words. So, yes, what else is there to say about this? So here is a very slight variation. This is called word-to-vec. So this was invented by one of the people you might know, Jeff Dean. He's most famous programmer in the world or something. Then he will actually come to Lausanne end of January if you want to come to this applied machine learning days. He also invented MapReduce, and that's interesting that now he's also moved to machine learning and work on things like that, how to find good word embeddings. So that's word-to-vec, and it's the same thing as I described basically. So let's look briefly again. We have this word D times another word word N. What we did is we just took the inner product of these two vectors, and we said that inner product should be the count, how many times they appear together, actually the logarithm of that. What we do here is almost the same thing, but it's even a bit simpler. So this is the real. This is for a real world in the real world appearing together with this word, and then we can also do the same thing for our word D with any arbitrary word. This is like a fake word. So here is word N prime, so that's just another word. This is any random word. So probably it never appears together with the one we care about. But what we want is that our word with the real word, which I just saw them together, I just screened through my text. I see them appearing together. So I want this to be a very high score. And the fake word, which is a randomly sampled one, which does not appear with me, I want this to be a low score. So probably a negative score. So if you think about this, this is actually a linear classifier. So yeah, if our word here is fixed for a moment, then what we're doing is we classify the other word, right, the WN. We want the real word to be recognized as real, and the fake one to be recognized as fake. So real, we want it to have a positive inner product. Remember, linear classifiers. And the fake one, we want it to have a negative inner product. Yeah, if that would be true, that would be super nice. And what's the really nice thing about this algorithm now is that you can do this while you just stream over the text. You don't even have to compute these counts, who appears together with whom, right? Now you just read through your text. Whenever you see a word, you do two things. You do one stochastic gradient descent update with this, with the real word next to it. So you update these two vectors. And then you also sample a fake word, and then you have this thing you want to be negative. So you can This is a loss function which is defined when you just go through your text. So no need to compute any matrices. This needs no memory at all. It's just a streaming algorithm where you have, okay, you need to remember your word vectors, sure, but this is your parameters you're learning. And whenever you see two words, you change their two word vectors. So it's a streaming algorithm. That's the cool thing. And this real versus fake is, it's the same thing as a linear classifier. And it's actually a very important concept, which is used, it's maybe the most cool concept in machine learning at the moment, that to try to distinguish real from fake things. Because this is another easy way where you can learn without having labels, right? Because you just train a thing to distinguish real from fake. You can do this with many things. I'm not going into details, so we don't have time, and there's a lot of engineering sometimes to make these things, but you can also do this on a video, like you can train this thing, the same idea as here, on frames of the video to see what really is the next frame. Is it a real next frame? Or is it just a random image from anywhere 2 hours earlier, so for the video? If you learn a classifier which can do this, has a positive output for real pairs and a negative output for fake pairs, then this thing must probably understand quite a lot about here a video, or like the physics in that video. Why is the person in the frame running from left to right, right? So if it's able to tell that a second later this is the real frame, then it understands that. So that's an interesting training signal which you can use to train any machine learning model, basically. And here the simplest thing is when we just use inner products, a vector with another vector. That's the kind of linear case. And if you do this for the words, then this is actually called negative sampling, by just sampling fake words. So yes. So. Okay, any questions on this? So we're not going into the math for this, but there's like 2 steps for every while you stream to your text. And you update your vector. Any comments? So. Fake against real. Okay. We are almost done with this. So one thing we really want to mention as well is that now we have only talked about words. So what do we do if we have sentences or entire documents? So that's also an important thing. Also, if you want to do this challenge, one of our standard challenges we offer is classifying tweets into negative and positive emotions. So there now you have a tweet which has several words. What do you do? What is your suggestion? Let's say you have word vectors, but now I have 7 words in my tweet. What's your suggestion? What could be good features for the whole tweet? What would be a suggestion? Yeah, one very easy thing to do, as you said, is to average the vectors over my 7 words. So just take these 7 word vectors, take the average, and pretend that this is what my text is about. This sounds very naive, but it's actually amazingly good. This is much better than bag of words, which I admit to what we discussed at the beginning. So yeah, this is actually much better than the bag of words thing we had mentioned earlier. Okay, a bit more high level. There are many methods now, and So here you can basically see what the task is, and if so, here you have this entire sentence. Wait for the video and don't rent it. That's my sentence. And there's a dot at the end. So maybe question marks are also words. They also have their own word vector if you want. Doesn't matter. So that's the input you have for one sentence. Each word and this corresponding word vector, which has length k. By the way, yeah, the ones which work best is again like 50 or 100. It's very similar as in the recommender system case. You can download them of different sizes if you want. Whatever is good enough for your application. The set of word vectors is quite a big matrix because as we said, there are 1 million words, and for each one we have 100 entries. So this can be gigabytes, but it's kind of manageable. Yeah. So for one sentence we don't have gigabytes, but here we have like 10 words, and each word has a vector of size 100. So. And that's our input, and now we want to get a representation for a sentence. That's a bit difficult because the sentences have variable length. Some sentences say the same thing in a short number of words, and some take a longer number of words. So the very simplest thing you can do is to average your word vectors, and that's actually what we have here. Just add them. And maybe again there is a smart weighting that the important words should count more, but just adding them or averaging them is very, very recommended, and also extremely fast. So then there's some other things to do, and this we're not going to discuss much, but you can actually use simple neural networks on top of these word vectors. So you don't worry about this yet, but there is actually a kind of an easy concept which takes a window of, let's say, 3 words, and this window of 3 is moving over your text. So wherever the window is, that's what we call a filter actually. So what it does, this green window is a bunch of fixed numbers. Well, we actually learned them, which is 3 times 100, and they get multiplied with their corresponding entries, and then that produces one number. So that's what we call it's actually called a convolutional filter, but don't worry too much about this yet. This will then come a bit in the last 3 weeks when we discuss neural networks, which will be by Rüdiger or Banke. So don't worry too much about this yet, but if you see it, then it's quite a simple method to yeah, actually this should be maybe the same color. So you apply it at the top, it gets 3 words, combines them into one number by just multiplying them with their weight and adding them up. Then you get also one number here. The next thing you do is so now the problem is, what's the issue? Because now we're still variable length, that's the issue. Some sentences are short, some are long. So here I still have 10, which is the length of my sentence. So I have managed to compress my sentence from 10 times 100 to just 10 numbers, which is kind of nice, but the problem is it's still variable length. So what people actually do here is they do the maximum. So just take the max entry, and now you have a fixed length representation. So this sentence was 10, but I can do the same thing for a longer sentence, and then I take the maximum over more things, I will just get one number. And then you just repeat this, do this many, many times for a fixed number of times, and that's how you get a representation. From variable length, you can get a representation to fixed length. That's what convolutional networks do, and that's actually the same thing is what convolutional networks do on images. It's exactly the same thing. There you also have this sliding window over 2 dimensions. Here it's a bit easier because there's only 1 dimension. We want to slide over the text and pick up a signal, and we take the maximum of that signal over all these positions of the window of size 3. How to learn these weights of these filters? That's another story that's going to come. at the end when we talk about neural networks. Why the answer is stochastic gradient descent, but the difficult thing is to actually compute the gradient. So that's not so easy. Okay, this is state of the art for text classification, basically. And this is, there are lots of libraries around. You can classify this. You can download this and play around with it. But it's not so much better than actually just adding up the word vectors, which is even simpler. So, okay. The downside is neural networks, we can only train supervised. So you will need a lot of data which has labels to train this. And the nice thing about adding the word vectors is that they are unsupervised, they're just available. That's just a little preview to neural networks. The last one I want to mention, this is actually much easier than neural networks. And that's actually really nice. This only came up 2 years ago as well. And this is again a simple kind of matrix factorization approach to classify, so it's supervised, right? So you can classify things, for example, documents. Classification of documents. And this bridges a bit the two things we had. We said, yeah, you want to have bag of words. That's an easy way to deal with documents or sentences. Just put a 1 wherever the words you have appearing. But you also want to use word vectors because they are much more powerful. So how can we combine the two? This is what fast text does. And the way this works is, so xn here is my sentence. That's how I represent my sentence. And this is the very easy bag of words representation which I use here. So x is this vector of a very large size in size of the number of words I have, which is 1 million typically. That's the size of the vocabulary V. And yeah, just put ones where I have words. So I'm classifying a document, right? So the document has 4 words. Maybe it's more a sentence. And everywhere else I put zeros. So bag of words for that input. And yeah, that's all we need. But that's still the old approach, right? This has nothing to do with word vectors. So now there is a bit more here. So what it does here, it's multiplying this by a matrix here. And this is a K by size of V matrix. So this is Z transpose. And yeah, what it does, this collects the word vectors. So the 4 vectors which actually appear in my document, if I multiply them with my x, then it's just picking them up and adding them. So far we worked our way from the right x. We had that bag of words, we had the word vectors, they just get added up. So nothing, yeah, why do I need this crazy notation just to add my word vectors? Okay, but that's what it does. So the green part here is the sum of the word vectors in my document. Now it gets multiplied with another matrix, which actually is a vector. And that's my final classifier. So now I have a fixed length document representation. And now I multiply with my final classifier, which says that this is a good document or a bad document. Or this is a relevant document or an unrelevant document. That's how all classification problems on text can be formulated this way. And mathematically, this is kind of interesting. Why? Because, well, maybe you would say it's not interesting because it's a matrix factorization, right? So if you train this thing, then we will try to find 2 things: the Z matrix, which are the word vectors, and this final classifier vector, which is also one of our optimization variables. So Z Z is this big matrix here. And these are my optimization variables. And I will just try to optimize this over all my sentences. And also, so here you have your label or target. Remember, this is supervised text classification. So for each document, we need to have the label if it's a good or bad document. That's the YN, and the document itself is the XN, the usual notation. What is F? Yeah, it's always a standard linear classifier. So that's actually the same thing you had at the very beginning for points. We have seen it just a few minutes ago when we talked about word2vec, because there we used this same kind of loss function. You can have like linear classifier for real versus fake pairs. And here we have a similar thing, but here we use just the linear classifier here is doing, is my document in the right class? So if it's the Y is +1, then the document should have a good score, a positive score, otherwise a negative score. So F is the linear classifier loss function, like in logistic regression. Or you could try hinge loss, like in support vector machines. I don't know if that has been tried actually. Somebody should try this. So, but the formulation they propose is with logistic loss. Okay, we sum this over all sentences, and now we just find the best W and Z. And it's interesting because, again, this is a linear function depending on its input, but the input itself is actually not linear, right? Because two things get multiplied. So that's why this classifier is quite powerful. It's much more powerful than if you just feed the bag of words into a standard linear classifier. Because here we learn two things together. We learn the word vectors together, that's the blue stuff. And we learn the classifier itself, that's the yellow, the W. And learning two things together is always better than learning them separately. That's called end-to-end training, right? You want to train the whole task, make the whole task work, learn the word vectors, so the Z variable is gigantic, 1,000,000 times 50. And the W matrix is very small, that's just a vector of 50, which is a classifier in that space of 50 coordinates. That's where the word vectors live. That's called a fast text, and it works super well. It's an open source library. You can download that. Okay, that's it for text today. There's some pointers here if you want. And next week we will talk about SVD.